Production or manufacturing of any object is a value addition process by which raw material of low utility and value due to its irregular size, shape, and finish is converted into a high utility and valued product with definite size, shape, and finish, imparting some desired functionality. Machining is an essential process of semi-finishing and often finishing by which jobs of desired shape and dimensions are produced by removing extra material from the preformed blanks in the form of chips with the help of cutting tools moved past the work surfaces in machine tools. The chips are separated from the workpiece by means of a cutting tool that possesses a very high hardness compared with that of the workpiece, as well as certain geometrical characteristics that depend upon the conditions of the cutting operation. Among all of the manufacturing methods, metal cutting, commonly called machining, is perhaps the most important. Forgings and castings are subjected to subsequent machining operations to acquire the precious dimensions and surface finish required. Also, products can sometimes be manufactured by machining stock materials like bars, plates, or structural sections. Methods of machining. In the metal cutting operation, the tool is wedge shaped and has a straight cutting edge. Basically, there are two methods of metal cutting, depending upon the arrangement of the cutting edge with respect to the direction of relative work tool motion. So there is the two picture. First one is orthogonal machining and next one is oblique machining. And the two methods of metal cutting is orthogonal cutting or two-dimensional cutting, and another one is oblique cutting or three-dimensional cutting. Orthogonal cutting. The cutting edge of the tool remains at 90 degrees to the direction of feed. The chip flows in a direction normal to the cutting edge of the tool. The cutting edge of the tool has zero inclination with the normal to the feed. The chip flows in the plane of the tool face, therefore, it makes no angle with the normal in the plane of the tool face to the cutting. The shear force acts on a smaller area, so shear force per unit area is more. The tool life is smaller than obtained in oblique cutting. There are two mutually perpendicular components of cutting forces on the tool. The cutting edge is bigger than the width of cut. There is a picture of orthogonal cutting and mention here chip, tool and workpiece. Oblique cutting. Cutting edge of the tool remains inclined at an acute angle to the direction of feed. The direction of the chip flow is not normal to the cutting edge. Cutting edge is inclined at an angle lambda, inclination angle, to the normal to the feed. The chip flows at an angle beta, chip flow angle, to the normal to the cutting edge. The shear force acts on a larger area, hence the shear force per area is smaller. The tool life is higher than obtained in orthogonal cutting. There are three mutually perpendicular components of cutting forces on the tool. The cutting edge is smaller than the width of cut. There is a picture of oblique cutting and mention here chip, workpiece, cutting edge inclination, chip flow angle and tool. Cutting tool geometry. Cutting tool is device with which a material could be cut to the desired size, shape or finish. So, a cutting tool must have at least a sharp edge. There are two types of cutting tool. The tool having only one cutting edge is called single point cutting tools. For example, shaper tools, lathe tools, planer tools, etc. The tool having more than one cutting edge is called multi-point cutting tools. For example, drills, milling cutters, broaches, grinding, wheel honing tool, etc. A single point cutting tool may be either right or left hand cut tool depending on the direction of fit. In the picture, this is a primary cutting edge, and see here, first one is left hand cutting tools and next one is right hand cutting tool. Cutting tool nomenclature. In the picture we see auxiliary cutting edge, tool axis, shank of tool, rake or face, principal cutting edge, principal flank surface, corner or nose, and auxiliary flank surface. The geometry of a cutting tool consists of the following elements: face or rake surface, flank, cutting edges, and the corner. Face or rake is the surface of the cutting tool along which the chips flow out. Flank surfaces are those facing the workpiece. There are two flank surfaces, principal and auxiliary flank surfaces. Principal cutting edge performs the major portion of cutting and is formed by the intersecting line of the face with the principal flank surface. Auxiliary cutting edge, often called an end cutting edge, is formed by the intersection of the rake surface with the auxiliary flank surface. Corner or cutting point is the meeting point of the principal cutting edge with the auxiliary cutting edge.